In this video, we're going to do vector loop analysis of a skid steer. This is also sometimes called a skid loader. So here, this piece of construction equipment has an attachment on the end right here to scoop up dirt. And then it's got the boom, that's this yellow piece, it has the cab where the operator sits. And then this cylinder along here is connected to the boom and then also to this spot down here. That's one of the actuators. The other actuator is what moves the orientation of the scoop. So 2 actuators, 2 degrees of freedom. So now we'll count up links, joints, figure out the mobility, how many loops we need, and then we'll draw out those vector loops. So first we'll draw kind of how everything connects. So down here we've got 1, 2, 3, 4, 5, 6 revolute joints on the bottom. And then we'll connect these. So here is a cylinder, has the prismatic joint, and then we'll connect these dots. Now the ground here is kind of all one link. And then we've got the boom. So that is all this. So now where everything attaches, we're going to draw this a little bit differently. So you see how the cylinder down here is connected to this beam, which actually goes through, say, about this joint right here, because we're kind of underneath the way the picture is drawn. So that cylinder acts in the middle there, but we'll draw it, since we're doing 2-dimensional view, connected here, here, here. So there is the cylinder. And then we've got this link there. So now we count up all of the joints. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 revolute joints. And then 10, 11 prismatic joints. So that is 11 total. And then we need to figure out links. So we've got the cylinder counts as 2. So 1, 2, and then we'll go just around. We've got the ground, which is 3. Then this connecting link here, which is 4, 5. The boom is going to be 6. The cylinder up here, 7, 8. Scoop is 9. So then number of loops, L equals J minus L plus 1 is going to equal 3 loops. So we'll have 2 loops down at the bottom, and then we'll have 1 loop up at the top. And then we can calculate degrees of freedom, or the mobility. M equals 3 L minus 1 minus 2J. So that's going to be 3 times 8 minus 2 times 11. (24 minus 22 equals 2, which matches with the 2 degrees of freedom because we have 2 actuators. So now we'll assign vectors to all of the links to get a vector loop diagram. We've got 3 loops, so we'll start with the bottom loop. So down here is our coordinate frame. We'll start there and go up along this cylinder, R1, and then we'll go from the origin up here. Say that is R2, R3, R4, R5, and then we got to do the second loop down here. So we'll say R3 and R4 are both part of that. And we've got this other link here, R12, and then going to the side, we have R11. So R11 and R2 are both part of ground. Put that in there. Now the cylinder is not part of the ground because it rotates down there at that bottom right corner, and then it's connected to the boom at that point. Here's another, got all of these rotational joints. So now we need to connect the top loop to the bottom loop. So we'll go up here, say along the boom like this. It's R6. And then R7. Now there's no joint between R6 and R7. Those are going to be related by a constraint. And then we've got the third loop. So this is going to be R8, R9, and R10. So now over here at the whiteboard, we'll get the vector loop equations and then figure out the knowns, unknowns, and inputs. So we've got 3 loops, the red loop and the blue loop down at the bottom and the green loop up at the top. So let's go clockwise around the top loop and counterclockwise around the bottom loops. So for the red loop, we start at the origin, then we'll go along R2, plus R3, plus R4, plus R5 minus R1 equals 0. Then the blue loop, also counterclockwise, we will be including R3 and R4 in that loop, as well as the R11 ground and the R12 extra link. So we'll say R3 plus R4 plus R11 minus R12 equals 0. And then finally for the top loop, we will go clockwise around this one. So we'll have R8 along the boom plus R9 along the scoop minus R10 along the cylinder equals 0. So from these vector loop equations, we'll be able to derive the position scalars, velocity, and acceleration equations. First, we need to figure out knowns, unknowns, and inputs. So the knowns are going to be anything that doesn't change. So that will be most of the links, actually all of the links except for the cylinders. So we know that cylinders will be our input. So our input is R1 and R10. All the other R's are known. So R2, R3, R4, R5, R6, R7, R8, R9, R11, R12, as well as some of the angles. So Our 11 here is part of the ground, and so is our 2. Theta 2, theta 11, both known. So now the unknowns are pretty much going to be all of the other angles. So theta 3, theta 4, theta 5, theta 6, theta 7, theta 8, theta 9, theta 10, theta 1, theta 12. Now a bunch of these are all connected on the boom. So let's see, R4, R5, R6, R7, and R8 are all connected. So these will be related by a constraint. Or should I say multiple constraints? We'll need to figure out those constraint equations. Because we'll need to get down, if we have 3 vector loop equations, we can account for 6 different unknowns. So we'll have theta 1, theta 3, all of the constraint thetas, we'll be able to group those. And theta 9, 10, and 12, that'll be our 6 unknowns. But we need to figure out what these constraints are. So looking at these, we can see that theta 4, this one has the lowest angle. So here is R4, and we'll just extend R4 that way. That's the direction that it goes in. Then R5, we'll have this one goes that direction. And then R6, we can see it on here. R6 will extend that direction. And then R7 and R8 point in the same direction. So we can knock out that constraint. Theta 7 equals theta 8. But we need to give some names to these other constraint angles. So let's say that this angle between 4 and 5 is beta. And then the angle between 5 and 6 is delta. And the angle between 6 and 7 is gamma. So I'm just going to draw this in the white part so it's actually easier to see, because right now it's kind of a mess. Here basically is the boom of the crane. And then we've got R4, R5. There are joints here. And then R6. R7, R8. Okay, so now let's put those lines in. So R4 points in this direction. R5 extends like that. R6 extends up here. So this angle is gamma. And then the angle between R5 and R4 is beta. And between R5 and R6 is delta. So now this should be a little easier to see here. So if we write out these constraints, then we had theta 7 and theta 8 are equal. So then theta 4 equals theta 5 plus beta. Theta 5 equals theta 6 plus delta. Theta 7 equals theta 6 minus delta. Sorry, minus gamma. So now these constraints are all kind of interrelated. But the easiest thing for us to do as far as calculations go will be to relate them back to theta 4. But we need to take derivatives. So we take the time derivative. Theta 7 dot equals theta 8 dot. Beta, delta, and gamma are all constants. So we'll just have theta 4 dot equals theta 5 dot. Theta 5 dot equals theta 6 dot. Theta 6 dot equals theta 7 dot, but then up we had theta 7 dot equals theta 8 dot. So basically all these theta dots are going to be equal. So that'll be handy when we're calculating the velocity unknowns. Same thing, all of their accelerations will also be equal. So now that we have figured out the vector loop equations, constraints, and knowns, unknowns, inputs, we need to figure out the position equations. So looking at this, the two bottom loops, the red one and the blue one, are intertwined. So those directly depend on each other. Calculating one is going to affect the calculation of the other. Now the green loop up at the top, that one is relatively independent of the other two. So its physical location in space will be dependent on the position of the boom, but the angles of R8, R9, R10 are not going to change relative to each other based on the position of the boom. So that loop operates separately from the others. So we can actually work this out in two parts. We'll work out the bottom loop, and then once we have calculated the bottom loop, we'll be able to use all those constraints to get us to the top loop, and then calculate the top loop. So the first thing we need to do is break the bottom loop vector loop equations, those red and the blue ones, into position scalars. R11 only points in the x direction, so we can get rid of it from the y equation and just simplify this. So this is position. Now that we've got position, we need to take the derivative and get velocity. Now remember that because theta 4 dot equals theta 5 dot, theta 6, theta 7, theta 8, etc. is all equal, we'll be able to work out some substitutions. But first, let's take the derivatives. Now note here that the R2 theta 2 stuff didn't have a derivative because R2 is part of ground, it's constant. And when we differentiate the R1 theta 1 stuff, because R1 is one of the inputs, is the actuator, R1 will stretch and theta 1 will change angle. So we have to use product rule and chain rule and those, and it comes out with two derivatives. So now let's move on to the blue loop. Now we can simplify these based on our constraint derivatives. So let's set all of the things that are equal to theta 4 dot, we'll just put that equal to theta 4 dot. So that will change theta 5 dot here to be theta 4 dot. And that's it for this loop. So now that we've got the velocity equations, we need to put them into matrix form. So matrix form is J theta dot equals B, and we'll set up those matrices. So J is going to be a 4x4. Theta dot is going to be a 4x1. And then B is going to be also a 4x1. So here is the theta dot matrix, here is the B matrix, here is the J matrix. So we'll fill out the theta dots, theta dot 1, theta dot 3, theta dot 4, and theta dot 12. Those are all of the unknowns there. So what goes in these equations, in the Jacobian then, is the coefficient. So we'll have the X, Y, and then we'll have the unknowns, theta 1, theta 3, theta 4, and theta 12 stuff. So we need to just fill in these coefficients. And finally, we will fill out the B matrix. That's going to be the inputs, which is basically everything left over. Although we know that R1 is the input because it's a cylinder, and the sign changes when we move it to the right side. It's okay that there are zeros in part of B as long as B is not completely empty. So now we've got velocity here. So next we'll have to take the derivative of velocity and get acceleration. So we'll take that derivative of those scalar equations and then we'll put it into matrix form. Note that we have a 2 in front of this final derivative. And that's because since we're using product rule and chain rule and R1 and theta 1 both change, then we end up getting 3 derivatives. Let's see, I'll highlight over here. So the R3 theta 3 stuff will come out with 2 derivatives from velocity to acceleration. Because R3 is constant and theta 3 changes. So we'll have that using product rule, we'll get the derivative of the sine component and then the derivative of the theta dot. So that'll be 2 different things. So that's what happens down here. Now, same thing for the R4 and R5 stuff. We also get a theta double dot and a theta dot squared term. Now, with the R1 theta 1, R1 changes as well. So we'll have an R1 double dot, shows up here. And then we'll have an R1 dot, which shows up here. And then we'll have the derivative of the cosine component. So that'll give us the second term that goes here. So that's why we have a 2. Then we'll have the derivative of the sine and the derivative of the theta 1. So we got the theta 1 double dot, and then we got the sine turned into cosine, we have a theta dot squared. So the y will follow that same exact pattern. So now that we've got these, we will put them into matrix form. So remember that the J matrix will be the same. The theta dot matrix will become theta double dot, and then B will be everything else. Now that we have knocked out the bottom loop, we'll do the top loop. So looking at this top loop, I'll draw it larger. We've got the boom of the crane is here. Then we've got that bucket on the end. And we've got these vectors. So we have R8, R9, R10. So R8 plus R9 minus R10 equals 0. We'll write out first the position equations. Now from position, we'll take the derivative and get velocity. Notice that R10 and C10, or like R10 and theta 10 both change. So that will use product rule. The R8 theta 8 and R9 theta 9 stuff, that will just be chain rule because R8 and R9 don't change. And now we'll put them into matrix form. So matrix form for this one, since there are only two equations, we'll have two rows in the unknowns in the J matrix, and then we'll have two unknowns, which will be theta 9 dot, theta 10 dot. Notice that theta 8 dot is not going to be an unknown here because we calculated it already from the bottom loop. It equaled theta 4 dot. We were able to figure that out. So it'll be on the B side. Since we already know what it is, it just kind of acts like an input. So B will also be a 2x1. And J theta dot equals B. So we get the coefficients of the theta 9 and theta 10 stuff. And we'll fill out the rest of it. So B will have everything else, which is going to be the R8 theta 8 stuff along with the R10 double dot stuff. Notice the sign change as we switch from the right to the left side of the equal sign. So now we've got J theta dot equals B. So this is velocity in matrix form. So we're almost done here. Now we just need to take the derivative of velocity to get acceleration and then put that in matrix form. Notice that the R10 theta 10 stuff, again, we will have to use product rule and chain rule there. So several derivatives out of that will end up with 5, and then 2 of them will combine, so we'll have 4 total with a coefficient of 2 in front of some of it. And then the R9 theta 9 stuff and R8 theta 8 stuff will only have to use chain rule there because R8 and R9 don't change, only theta 8 and theta 9. Now that we've got the scalar equations, let's put those into matrix form. So remember that J will be exactly the same. Theta dot will become theta double dot, and then B will have everything else. so here is acceleration. So now we've worked out position, velocity, and acceleration for all 3 loops of the skid steer. So now let's take a look at the simulation and how I actually programmed that. So here we are in Matlab. You can see I started out with defining all of the constants and all of the constraint angles. Then I put these constraints here just to remind myself what they were. Defining the inputs. So R1 and R10 are our inputs. So that's here, figuring out how far that should go, and R10, figuring out how far that should go. So then we pre-allocate arrays, define the initial guesses, solve the first loop. So here, the first loop will get solved, and that is basically just the bottom loops. So we have x1, y1, x2, y2, and you can see those correspond to the red and the blue. So those loops solve, and then that comes out with the answers here: theta 1, theta 3, theta 4, and theta 12. So once those have all been calculated, then we get velocity, we get acceleration. Finally, the bottom loops are finished. So the next thing we do is calculate the constraint angles. So that right here figures out that theta 5, theta 6, theta 7, theta 8, all along the boom. So then we can use that to travel from the bottom loop to the top loop. So here we are at the top loop, and this is the R8, R9, R10 loop. So it's smaller, it's a 2x2. We can figure out what theta 9, theta 10 are. Calculate velocity, calculate acceleration, and then finally we plot. So let's run it. Okay, so looking at this, the joint positions, we can see all of these different thetas. So R1 and R10 are on the X and Y axes. Those are the inputs. And then positions in radians is on this Z axis here. So you can see that everything looks pretty smooth. It all looked pretty smooth during the simulation, and all of these angles are different. And that's good because except for theta 7 and theta 8, which theta 7 is not shown on here because it's the same as theta 8, then all of the angles are separate. We'll see a few of them that do look like they are related by constant values here, and that's good, they should be. So well, let's look at velocity. So the velocities here, you see there aren't as many lines, and that's a good thing because theta 4 dot, theta 5 dot, theta 6, 7, and 8 are all the same velocity. So that's how come you don't see as many lines, because they're underneath each other. Same thing for joint accelerations. We don't see as many lines because theta double dots, 4, 5, 6, 7, and 8 are all the same thing.